Hi, good morning. Today's session, what I wanted to do was kind of spend some time with neural networks, but a clear, disclaimer here that it's okay even if you don't understand what is happening behind neural networks, because essentially it's all a black box. What we would have seen with the videos also. We will see some of the steps, some of the background steps that happen with the neural network, but in the end, what is the exact calculation that happens, like with the random forest and cart, we knew that it's calculating gene index, and you were able to explain why you're getting a particular output. With neural network, there's nothing like that. You cannot explain why you're getting a particular output and stuff. So we'll try to see what are the different steps that happen, but in the end, if we do not understand all the steps perfectly, it's totally okay, because you'll get the output, but um, you will never be able to explain why you get a particular output. And if you run the same commands, you would have seen that with the videos as well. If you're running the same command with the same data set multiple times, you'll get different outputs, because apparently the weights that neural network is giving to the input variables will change each time. So even at the same time, if two people are running the same command with the same data, everyone will get a different output. Okay. So apart from that, what we'll do is, if you would have seen the HR attrition data set that was uploaded this week for practice, so that is again a data set, huge data set which can be used to apply all the machine learning algorithms. It is pretty much similar to the data set that you guys have for your mini projects. So I won't be applying all the algorithms there today to exactly tell you what are the commands that you need to apply for the mini project. But at the same time, there is an essential step of exploratory data analysis, which we kind of did with some of the lectures, the basic one. But this time, since the data set, both the data sets, the HR practice data set and the data set which you've got for your mini projects, both of them have multiple columns, so it becomes essential for us to be able to choose which variables should be used for the models. Sometimes some of the models that we use have the ability to choose the best variables that are there, but nevertheless it's always a good practice for us to study the variables in the first place, each variable one by one, and then choose from our logic whether or not we use those variables in the models. So we'll spend some time in seeing how do we decide whether or not a variable should be used in the data set. We'll do that using the HR attrition data set, just the exploratory data analysis part. So keep that in mind, that you don't need to go to the models directly. You need to do exploratory data analysis as a first step before you apply any of the machine learning algorithms. Okay, and when we meet the next time, that will be, I believe, 2 weeks from now, when we do the solution of the mini project. With that solution, we'll also do the complete solution of the HR attrition data set as well. So with neural networks, we'll start off with seeing briefly what a biological neural network is. We won't go into much of the details. We'll just do an overview, because it helps to understand what an artificial neural network does. Then we'll see the overview of artificial neural network and a small example, a pretty small example on what happens and how a neural network learns. We'll see how we implement AAN and different steps that are a part of implementing artificial neural network. One of them being back propagation, then the weights updation, and then the error function. Then we'll also see the summary of what the overall learning algorithm that the neural network follows. And then we'll see how we implement neural network in R using the same using that same iris data set that we used to do, so that we only know what is the essence of using neural network in R, and we're able to compare the outputs of what we did with previous algorithms and what the neural network gives us. Okay. So with biological neural networks, you would have seen already how they're the basic building blocks of the the central nervous system. So these are the diagrams which may be repetitive for you, but then they help us understand what a biological neural network does. So not going very deep into biology. So something that you see in yellow is a neuron, okay, which is similar to a neuron in the artificial neural network, wherein each contains some data about the input data variables. Okay, so like the neurons are interconnected at the point called synapses. So in the diagram above, you see red circle where there is a synapse. So neurons are interconnected at the point called synapses, and this is similar to the artificial neural network, because the different input variables that you take, that information is passed to the hidden layer, and how that information is passed to the hidden layers is through a point which is similar to the synapse in the biological neural network. So there are three parts that are typically present in a biological neural network. One is the dendrite, which is the yellow you can say like terminals of a neural network, which are responsible to receive signals from the surrounding neurons. Then there are axons, which are nothing like a path. So comparing it to the artificial neural network, like there is a path when you go from the input layer to the hidden layer. There is a path in between which carries the information. So the axon is similar to that. Then the synapses are responsible for receiving the signals and learning from the past activities. How we correlate it to the artificial neural network is because if you know of the concept of back propagation, even the artificial neural network learns from its past activities. Hence, you're able to kind of relate the biological neural network with the artificial neural network. So each of the neuron here acts as a neuron in the artificial neural network. The axons act as a path where the information is traversed from one layer of neural network to the another layer of the neural network. Then the dendrites and synapses are used to send and receive information between one neuron to the other, and then they also enable the neural network to learn from the past activities, and that's how the algorithm improves itself. Okay, so this is essential to understand only because the artificial neural network gets its name from the biological neural network only. Okay. So this is again a small diagram to just show you how the information is passed with the biological neural network, and a similar kind of thing happens with the artificial neural network as well. Okay, so what happens is whenever a certain information is coming to a neuron, when a certain information is present in a neuron, so there's this thing called threshold, which we're also seeing with the artificial neural network. So once that threshold has reached, that threshold has been achieved, the neural network transmits a signal through the axon. And the similar kind of thing happens with the artificial neural network as well. Whenever the threshold is reached, activation function triggers, and then an information is passed from the input layer to the output layer. So we'll see how each of these steps in the biological neural network helps us also understand what is present in the artificial neural network. Okay, so this is how a basic of how an artificial neural network works. So the inputs that you see here are nothing but the input data variables with the data set they are working with. Then there are certain weights which are applied to each of the input variables. So the weights that are applied are nothing but they help the neural network to tell what is the importance of each of the variables. So this is also what we saw with the previous algorithms we learned. So each variable that is present in our input data set does not have equal importance. Okay, each input variable does not have equal importance. There are variables which are more important, there are variables which are lesser important. How that is decided is through these weights. So whichever variable is given a higher weight is comparatively more important than a variable which has a lesser weight. So this is how the weights are used in a neural network. So the set of inputs which are nothing but the variables from the data set are thought of as neurons. This is how we correlate an artificial neural network with a biological neural network. So then they are weighed according to the weights that are applied, what I just told. And finally, this is we do kind of a sum product of the input variables with the weights. Sum product means to say x1 into w1 plus x2 into w2 plus x3 into w3 and so on. Okay, so the function that you see here, the summation function or the sigma function here, this can also be called as a transfer function. So this actually performs the sum product. So it will sum up the weights and the input that it receives from each of the neuron. The next step is to go to the activation function, which will decide whether or not a neuron will fire. So this is similar to the biological neural network, wherein with the threshold, we decide whether or not the information should be sent to the next layer. Okay. So if the threshold, so whatever sum you get using the transfer function, you compare it to the threshold. If it exceeds the threshold, the activation function decides to fire. When it fires, the information is passed from the input layer to the output layer, like similar to what happens in the biological neural network. When the activation function fires, information is passed from one layer to the other. Okay, so like I told earlier also, the weights can be used to amplify or de-amplify the original input signal, meaning to say they are used to determine how each variable will be used, what is the importance that will be given to each of the variables. Okay, so consider a simple example. So this example has got nothing to do with the neural networks actually. Consider that you have just say two input variables x1 and x2. So these are two input variables in a data set, one of them having a value of 0.6 and one of them having a value of 1. And the weights say that are applied to both of these input variables are 0.5 and 0.8. Okay, and you've also been given a threshold of 1. So what happens in simple terms in the neural network is the first step of a transfer function, what we saw in the previous slide. So nothing but a sum product will happen here. So 0.6 into 0.5 plus 1 into 0.8. So that gives you a 1.1. So this is similar to the summation function that we had seen here. Next, we compare this value that we've got with the threshold. So say our value that we've got is 1.1, but the threshold is 1.0. So we see that our output is more than the threshold that was allowed. So since the output is greater than the threshold, so the neuron is activated and it fires. Okay, so this is a very simple example. This is not what actually happens in the neural network, because there a derivative of the error function and all that is calculated. So error function is nothing but the actual output, a difference between the actual output and the desired output. So therein a derivative of that is calculated and passed back to the neural network, but I put this example only to show you how the threshold works. So whenever the output exceeds the threshold, the neural network will know that it needs to fire um, a signal. What is meant by firing a signal is nothing but a back propagation, meaning to say that whenever an output increases the threshold, um, the algorithm will sorry, whenever the output increases the threshold, a back propagation will occur and a reiteration will occur, a new iteration within the neural network will occur, and the output, the algorithm will try to improve the output. Okay. Now we'll see how we implement the artificial neural network. So this is a simple diagram to show how a neural network works. So there are, for example, 3 input variables and 2 output variables here. So there can be any number of hidden layers that are present in the neural network, and the hidden layers actually perform whatever the algorithm needs to be applied is done by the hidden layers only. There are different ways on how we decide how many hidden layers are to be present, and we'll see that when we work with R. So what happens here is that the input layer will take the input from the input variables. So say you have 3 variables here. So each input, each of the neuron that you see in the input layer will have data from 1 variable each. The input layer will take input from the input variables. The hidden layer will help the input layer to move to the output layer. Okay, so the input layer will pass the information to the hidden layer with the weights present, and then the hidden layer will move that data to the output layer. But the hidden layer is essentially a big black box layer, like I told you earlier. You will never be able to understand what is happening with the hidden layer. And the output layer will throw you the final output. So this is another way to a more detailed diagram of the above diagram. So what I'm trying to show here is that there could be any number of nodes that one can be present at every layer, and then there are weights that are applied to the inputs. Excuse me. Okay, so then there are weights that are applied to the inputs that take them to the hidden layer. So if you see in the diagram below, there are 3 inputs, 1, 2, 3, and then there are some weights which are applied to the each of the inputs when it is being taken to the hidden layer. So each input variable with some weight applied will go to each neuron in the hidden layer. So if there are 3 input variables and there are 3 hidden layers, so each of the inputs, like the input I1 will go to each of the neuron in the hidden layer, and a different weight will be applied when it goes through each of the neuron in the hidden layer. And there is another category of weights. So one is the weights that are applied to the input variables. There is another category of weight which we call as the bias values. So bias values are again used to train the neural network. So this can be compared to, if you remember, with the regression also, we used to have a similar thing wherein we'll have some weights that are assigned to each of the variables. So that were the coefficients back in regression, when you used to get an equation something like y equals to a plus b1x1 plus b2x2 plus b3x3 and so on. So when there were coefficients in regression are the weights which are in the neural network, but there was also an intercept which was the unexplained variance or unexplained output that the intercept used to capture. So similar happens here with the hidden bias. So if there is some information that the input variables along with the weights cannot capture, that is captured by the hidden bias. So with each of the layer that you have apart from the input layer, there'll be a bias added. Like if you see in the diagram here, with the second layer, that is the hidden layer present in the between, there's a hidden bias that is added. And with each hidden layer that you have, like here we have just hidden layer, but with each hidden layer that is present, there'll be a hidden bias for each of the layers. And finally, there will also be an output bias which is present for the output layer, nothing but the intercept what we used to have with the regression equation. Okay, that was the basic of what an artificial neural network does. We'll go to back propagation now to see how the neural network learns. Okay, so the basis of a neural network is a powerful learning mechanism. Although it is a powerful learning mechanism, but you will never be able to understand what that learning mechanism is. But that being said, the neural network has a powerful learning mechanism, and it can learn any function given it has enough hidden units. So each of the hidden units that are present enable it to learn to the input data set. And how it learns is by the mechanism that we call as backpropagation. Okay. So like I told you earlier also, when an input is fed to the neural network, that is when the input variables are fed into the neural network, the input some weights will be applied to the input that is coming. Some bias will be applied to the in addition to the input that is coming, and finally that data will go to the hidden layer. The same process will be repeated and the data will move to the output layer. When you get the data at the output layer, the difference between what the actual output or the desired output was and the output that you are getting, some error will be calculated based on the difference. Whatever is the error will be fed back to the first layer, and the whole process repeats again. Okay, so these errors are fed back to the neural network, and then these weights, to the question that you were asking, the weights are then changed in order to try to reduce the errors and give the correct output. So in the first iteration, random weights will be assigned, but with each iteration that happens, the weights are changed using the errors that we have got in the previous layer. So this is the diagram that explains back propagation. So there are some input variables, then there is a hidden layer. So say there are 3 input variables here, then there are 2 hidden neurons with the hidden layer. So each of the input variables is being fed to the hidden layer, and then there's also a bias which is being applied, and then from the hidden layer we're going to the output layer. At the output layer, the error calculation happens, which is nothing but the difference between the actual value and the calculated value. Whatever is the error calculation is back propagated, and then the weights are modified. This happens each time the algorithm runs, and that's how the weights are improved, and that's how the algorithm learns. Okay, so then once you're done with back propagation, so all you did with back propagation was to get the error and pass it back to the input layer so that the weights are modified. Now how the weights are modified is, after you've done the back propagation, you need to update the weights. Now if you remember with the previous slide that we've seen here, there are weights applied to the hidden layer, and then there are weights applied to the output layer as well. So both of these weights are different. Okay, so don't get too confused with what the equation here is, but this is just meant to show that there are 2 different weights that are applied to both of the layers. So Wij that you see here is the weight that is passed to the variables from the input layer, and wjk is the weights that are applied to the neurons from the hidden layer. Okay, so both of them will learn from the errors that they are doing, and both of the weights will be updated. Don't go very deep into what the mathematical terms here are, but this is just meant to tell you that both of the weights will be modified based on the error that we are seeing from the previous iteration of the algorithm. There's another thing which you would be which is seeing here, which is the alpha value. So alpha value is nothing but the learning rate. Learning rate means to say at what rate do you want the neural network to learn. So this is nothing but the learning speed. Okay, if you make the learning speed too quickly, or you make the alpha value, you don't really specify these values, this is what happens in the background. But if the learning speed is very quickly, the learning speed is very fast and alpha value is closer to 1, the algorithm would not be able to learn properly. This is nothing but trying to say that you're trying to learn something very quickly, so you just run over it, you don't understand the essence of what was there in the data. And if you make the learning rate very small, you don't allow the algorithm to grow, you don't allow the algorithm to learn only. So an optimal learning rate is chosen, but you don't choose it, the algorithm chooses it itself. But an optimal learning rate is chosen for each iteration that happens with the neural network. So when backpropagation will occur, some errors would have occurred, and then a backpropagation will occur. That error will be passed back to the algorithm. The weights that are being passed, that are being applied to the input data variables will be modified. The weights that are being applied to the hidden layer will also be modified, and finally a new output will be produced. And this process repeats across multiple iterations, and each time the weights will be updated. Okay. Then we come to the error function. Error function is nothing but again the difference between the actual value and the desired value here. So although this is a repetition, but the input variable will be passed to a system. So adaptive system here is nothing but the hidden layer, and then you get a output y. You compare that output to the desired output. Whatever is the error is passed back to the adaptive system, nothing but the hidden layer. Then the weights are modified. So one thing to keep in mind is that the error should satisfy some particular properties. This was present in the videos as well that we saw. The first thing being that the error should be derivable, meaning to say that it should be possible to do a derivative. Derivative is nothing but d by dx, what we used to do back in 11th 12th mathematics. So it should be possible to do a derivative. Why? To answer to one of the questions earlier, the threshold that we calculate, the threshold that we specify is a derivative of the error. Okay, so if it is not derivable, so the threshold thing will not work. The threshold that we are specifying, that we are telling the algorithm, is nothing but derivative of the error that we are getting in each layer. Okay. So this is very obvious although, but as the output moves towards the desired value, the error should obviously move to 0. Error should be negative, again for the reason that we should be able to do a derivative of it. And then we need to choose the error value. Sorry, we're not choosing the error value actually, but then when there is a too low value for the error, or there are too high values for the error, that actually impact how the neural network works. If the error value is too high, the accuracy of the neural network will be bad, and then it will take a lot of iterations to be able to learn. And if the error value is too small, sorry, that I've put it opposite. So if the error value is high, then the neural network will take a long time to learn. I'll just change it after this session. Okay. So we'll finally see an overview of what happens with the learning algorithms. The learning algorithm overall. So the back propagation actually allows the neural network to get trained, similar to how we train all the machine learning or the data mining models. Similar way, the back propagation allows the neural network to learn. This happens in multiple iterations, what I've been calling so far. These iterations in terms of neural network are also called as epochs. So it goes through several epochs before the network has sufficiently learned to handle all the data that is provided. This is again a different diagram shown in a different way to show how backpropagation works. But that will happen. That will happen for each of the iteration or each of the epochs. The input data will be fed, the output data will be compared against the desired value, and then it will be whatever the error will be back propagated using the error to update the weights. Now when will this stop? Meaning to say that each time when a particular error is calculated based on what was the output versus what was the desired output, and then a back propagation occurs. So this process keeps on repeating. So like we used to have a pruning step or a stopping criteria for the decision trees that we saw last week. Similarly, there should be a stopping criteria here as well. So multiple stopping criteria can be used for neural networks, one of them being a desired mean square error, and one of them being elapsed epochs. Desired mean square error tells what is the error that we can allow the data to have, what is the flexibility that we're giving the data to have, and elapsed epochs is nothing but what is the number of iterations that we want. So a neural network cannot run indefinitely through 10,000 or 1 lakh iterations. This varies with the data that you have, but it cannot run indefinitely. So we need to specify the number of iterations for which a neural network should run. So both of these are used as stopping criteria for the neural network. Okay, so again, I'm using the iris data set that we had seen with the previous algorithms as well. To give you a quick revision of what the iris data set was. So this data set has 150 entries, in which there are 4 input variables, which are sepal length, width, and petal length and width. And finally, there are 3 species, 50 of each species. And the aim of this algorithm is to try to predict what is the species of a particular flower given its attributes of sepal and petal length. So with the last session, we tried to predict the species using CART, using random forest. We also saw the same example with clustering as well, wherein we were trying to use the sepal length, width, and petal length and width to try to cluster these flowers together. So we'll use that same data set. I'm repeating the steps what we did earlier of generating a random number, shuffling the data. So this again is a optional step, but I normally do it so that there's no biasness which is present in the data. One important step which you can note down here is the line number 12 that I have with the R code. So if you remember with neural network, this was being done in the example that we did, and this will also be useful in the example that you do with your mini project. So if there is any variable which is categorical variable, something like the species that you have here, where it is setosa, versicolor, and virginica. When you have 3 species, you cannot have the data in this format when you work with neural networks. So you need to have 3 columns which are in forms of 1 and 0. So either you can do that with multiple commands, either you can create 3 new input variables and then pass 1 and 0 here. But a simple command is the class dot int command, which you can use in one go to create all the 3 variables. Let me show that to you how it happens. So if you see here, with a single command, I'm able to segregate the initial species that I had. If you see, the species I had here was in the form of Setosa virginica and versicolor, and then I've split that data in form of 0 and 1 with one single step. Okay, so what was done earlier was we used to do that for each of the variables one by one, but using this command you can now very simply split the data in the required format. Okay, and as a shortcut, what I've also done is I've done the scaling in the same command here. So what I essentially did was, from the initial IRIS-R data set that I had, I scaled the first 4 variables. So the first 4 variables of sepal length, width, petal length, and width was scaled, and then this width, the output variable, which was 1, was split in the form of 0 and 1 to be able to fit the neural network. So then I am simply dividing my data set into training and testing data set. So roughly a 70-30, but not exactly. So first 100 I'm passing to my first 100 rows I'm passing to my training data set, and next 50 to my testing data set, and finally I'm creating a neural network. So we'll see here what is the parameters that we pass to the neural network. So the first thing is the formula that we need to give here. So the formula here tells me that these 3, which now become my output variables, see Setosa, versicolor, and virginica, which now become my output variables, are a function of 4 independent or the input variables. So this is the formula that I've specified. Data is the training data set. Hidden specifies the number of hidden layers that you want. So a thumb rule to choose the hidden layers is under root of the number of input variables that you have. So if you have, I had 4 input variables here, so I chose 2. Okay, and since you saw you can have multiple hidden layers here, so say if you have maybe like here I had, 1 second, input variables and hidden layers. So since I had 4 input variables, I did a square root of this to choose that I'll have 2 hidden equals to 2 here. Give me a second. Okay, and sorry, so 2 here means I'm rounding it off to get a 2, so that will mean that I have 1 hidden layer with 2 neurons. Say you have maybe 20 input variables of in place of 4, so you do a square root of 20, which will be 4.47. Now you round it off to 5, then you do a square root of 5, and that will be 2.23. So you can round it off to probably 2 or 3. So what I'm trying to tell you is that when there are 4 input variables, I'll have just 1 hidden layer, which will have 2 nodes. When you have, say, 20 input variables, you'll have 2 hidden layers, the first of which will have 5 hidden neurons, the second of which will have 2 neurons. Okay, making sense? Like if I have 100 input variables, I'll have first hidden layer, which will have 10 neurons. Then I'll have second hidden layer, which will have 3 neurons. Then yeah, so that will be here. Say I have 500 input data variables. So I have first hidden layer, which will have say 22 hidden, sorry, I'll have first hidden layer which will have 22 neurons. Then I'll have second hidden layer which will have 4.7, or you can round it off to 5 neurons. Then again I'll have third hidden layer which will have 2 neurons. So this is how you decide the number of hidden layers that you have with the data and number of neurons that will be present in each hidden layer. Let me kind of erase this and do this again. Okay, so input variables and then the hidden layers. So when I had 4 input variables, I do a square root of 4. That will be 2. So I have one input layer which has, so this will be the first hidden layer with 2 neurons. Okay, so you kind of keep doing the square root multiple times. So I'm doing a square root here the first time. Second time when I do a square root of 2, I come to approximately 1. So then I stop. Okay, meaning to say when I have 4 input variables, I get a 2. So that will be first hidden layer with 2 neurons. Say if I have 10 input variables, I'll do a square root which is approximately equals to 3. So I'll have a first hidden layer with 3 neurons. And then I'll do a square root of 3, which is 1.7, and you can round it off to 2. So I'll have a second hidden layer with 2 neurons. Okay. Now if you do a square root, you keep on doing the square root iteratively. So now if you do a square root, you will get something like 1.4 or something. So there you stop. So with 10 input variables, you'll have 2 hidden layers. So with the hidden layer parameter that you're specifying here, I did a 2 here because I had just one hidden layer. So you need to give hidden equals to 2 here. With the 10 input variables, you need to give hidden equals to C of 3, 2. 3 means first with 3 neurons, second with 2 neurons. Okay, like a bigger example, if we take, I have 500 input variables. So I do a square root of 500. That will be say 22.36, and I'm rounding it off to 22. So I'll have first hidden layer with 22 neurons. Then I'm doing a square root of 22. That gives me 4.69, and if I round it off to 5, so I'll have a second hidden layer with 5 neurons. Then I do a square root of 5. Square root of 5, which gives me 2.23, so I round it off to 2, for example. So then I'll get a third hidden layer with 2 neurons. And then when I'm doing this with R, I'll give hidden equals to 22, 5, 2. So this means 3 layers, first having 22 neurons, second having 5 neurons, third having 2 neurons. Okay. So next is the threshold. So threshold is nothing but a derivative of the error that will be calculated at each step. So we can also see that from the help in R. See the threshold. So threshold is numerical value specifying the threshold for the partial derivative of the error function as a stopping criteria. So at each step, some error will be calculated as a difference of the actual value and the desired value, and then you calculate a derivative of it. So say the error in the first step is 2, for example. So you calculate a derivative of it, then backpropagation will occur, then a reiteration will occur, and this process keeps repeating. So this threshold equals to 0.01 says that keep repeating until you receive a derivative of the error function, which is 0.01. Okay. So in the first iteration, maybe derivative of the error function will be, say for example, 1. Then you backpropagate, reiteration occurs, then the derivative of the error function maybe comes down to 0.9. Then you repeat it, backpropagation occurs, then maybe the derivative of the error function comes down to be 0.6, then 0.2, 0.1, and till it comes down to 0.1, you need to keep repeating the algorithm. Okay. The next step is, so this is one stopping criteria. Threshold is one stopping criteria. Step max tells you what is the number of iterations you want. It is possible that even with 10,000 iterations or 10,000 cycles, the threshold doesn't reach 0.01. Doesn't mean that you'll keep running this algorithm infinite times. Step max is another stopping criteria, which tells us what is the number of iterations that we can allow a neural network to have. So step max equals to 2000 tells us that we need to, we can run this algorithm a maximum of 2000 times. Okay, so linear output equals to false is nothing but telling whether or not you want the activation function to work. So to revisit, activation function was nothing but allowing a neural network to fire a trigger. Firing a trigger means allowing a neural network to backfire. So, sorry, backpropagate. So when you specify linear output equals to false, that means that you're allowing the activation function. Okay. With the lectures, there were different activation functions that were also given, but there is not much difference, practically speaking, with the different activation functions. And even if you don't specify it explicitly with your commands, you're not missing out anything. Just specify that linear output is equals to false. This is enough to tell R that you want the activation function to work. Okay. Then life sign equals to full and life sign dot step equals to 10 are again optional steps. These are only to tell R that, say I am telling here that I want 2000 iterations. So these two steps are only to tell R that I want to see the output after every 10th iteration. If you skip this step, even then the algorithm will run, but it will not show you what is happening with each step. So when I'm telling R that I want the life science step to be 10, so after each 10 iterations, like after 10 iterations, after 20, after 30, after 40, so on till 2000, R will show me what is happening with the neural network. If you skip this, it will directly give you an output. Okay, then error.fct is nothing but telling you how do you calculate the error function. Okay, so error function is nothing but difference of the actual value and the desired value. But how do you calculate it? SSE is sum of squares error, and this is the best you can do with neural networks, because with neural networks you want your error to be positive, so that you're able to do a derivative of it. So the best thing to use is an SSE, which is sum of squares error. So supplying all these parameters, when I run this command, sorry. Okay. So I ran this command. See, there are two hidden neurons. That was what I had specified with each iteration. So I told that I can do a maximum of 2000 steps, but my algorithm stopped with 125 steps. So when there were 10 steps, when 10 iterations had occurred, my error was 2.869. After 20, it reduced to 2.795. After 30, it reduced to 1.487. And finally, after 125 iterations, my error reduced to 0.03541. So the stopping criteria which worked here was this threshold. So a derivative of 0.0351 would have been lesser than 0.01, and hence it stopped here. Okay. So once the error of 0.03541 was achieved, this was achieved with 125 steps. So I did not have to do 2000 steps. I got the output with each 10 iterations. You see, you could have done a life sign step of 1 to see what happened with each iteration, but then it becomes too detailed. So with each 10 iterations, you see the error was reducing, and finally it came down to 0.0351, and this occurred in 17 seconds only. Okay. Now if I kind of try to plot the neural network, this is what I get. So see, there are 4 input variables: sepal length, width, petal length, and width. I have just one hidden layer that has 2 neurons. These are the weights, the ones that you see, 1.83 on the top. Second. Yeah, so this 1.3 that you see, 1.83 that you see here is the weight. These are all the weights that you're seeing. Then the 6.6 that you see here, the -12 that you see here, sorry, these are the biases. So 1.83, 0.76, the one that you see on the black lines are the weights that are being applied to the input variables. The ones that you see in blue, 6.6 and 1.2, these are the biases which are being applied. So there's just one hidden layer with 2 neurons. The biases are being applied at both the layers. The weights are being applied to both the layers, and finally an output is being thrown out. Okay. One thing to note here is that if I run the same command again, the weights will be different. Okay, so if you run the same command at the same time with me, even then this will be different. So far what is happening is iris_n is a neural network model which is being created. It's just showing you that these were the 4 input variables, these were the 3 output variables, and something is happening and this neural network is getting trained. Okay. One additional step which can be done here is not with the small data set that I'm using, but if you have larger data sets, one another parameter that you can pass with the neural network command is this parameter called start weights. Okay, so what this is doing is that even though with back propagation the errors are being passed and then the weights are being modified, but additionally you can also pass the weights of the first step to the second step, meaning to say whatever were the weights that were being applied in my first step, I can also pass them as a parameter when I'm back propagating to the second step, so that the same weights are not being used. So this becomes an additional learning for the neural network. So this is not applicable in the small data set that I'm using, it won't do any benefit. But for the larger data sets that are present, these steps become helpful, and I'll show you how you do that. So you create another variable, old weight, or you can name it anything. And in the iris underscore n was the name of the model that I've created that has some weights. So I'm passing those weights to a new variable, and then I can create another neural network which has the same parameters. Additionally, I'm adding a parameter called as start weights, in which I am passing the old weights, that is the weights that I received in the first iteration. So this is an additional step you can do to improve the performance of your neural network. Okay, so far with iris underscore n, I've just created a model. Now we'll see how does our model work. Okay, so what I'll do here is with the data set here, I had used the training data set to create a model. Next, I'll be using the test data set to see how my model performs. So because I had scaled my training data set, so I'll also be scaling my testing data set and try to predict the outputs of the testing data set. So I'm using a compute function to predict the values of the output, the testing data set. Iris underscore n is the model that I had created, neural network model that I had created. And the data that I'm passing is the test data set. First 4 columns, which are nothing but the sepal length, width, petal length, and width. Okay, so finally, when I try to predict the values of my test data set, this is what happens. Now, since this is a scaled data set, so the numbers are achieved in this way, but you can again use these numbers as well to also do a prediction. Let's see how do we do that. So you see we had 3 species which were possible, and in the results that I get these are 50 entries which was in the test data set, and I get some scores for each of the species. Like for this particular flower, I get 3 values for each of the species. So the probability that it is a setosa is 0.001. The probability that it is versicolor is 0.01, whereas the probability that it is virginica is 0.99, which is 99%. So this flower, which is in the row number 131, will be a virginica. Similarly, the flower which is in this row 10th will be a setosa. The flower which is in row 95 will be a versicolor. The flower which is in 142 will be again a virginica. This one will be a versicolor. So what I'm essentially doing here is I'm trying to use the neural network model to predict what will be the class of my flowers in my testing data set. Okay, so pass the testing data set. I pass the neural network model, which contains the learnings that it has from the training data set, and I'm using this to predict. So this is the main step. Do not get confused with the other steps, because I'm just doing kind of formatting to give you a nice looking output there. But with this step, I'm trying to predict the values in the testing data set using the learnings I have from the neural network model. Okay, so with the results that I got here, I'll kind of try to compare it. So these are the predictions that my neural network model is making. These are the predictions that I'm trying to make for my testing data set using the neural network. But I should also be able to compare it to the actual values to see how good my neural network is doing. Okay, what I did with this step was nothing but I tried to, like I was telling you theoretically here, on how this would be a virginica and this would be a setosa and this again will be a versicolor. So I kind of tried to put that in words so that we don't have to read through the numbers. So these three commands that I'm doing here are doing nothing but producing this result from this result. So the first one should be a Virginica, the second should be a Setosa, the third should be a versicolor. This is what I'm doing here, telling R that whichever is maximum out of the three columns, I want that column name to come in my result. So this is the result that I get as a result of prediction after my neural network for the 50 entries that I had in my test data set. These are the predicted species of the flowers using my neural network model. Now I'll be using these 50 predicted values against the initial against the actual values to see how good my neural network is doing. Okay, so these are the original values which were present, and these are the values that I've got, and we'll finally compare them in the table. So you see we have out of 50, so this matrix, if you don't know it already, we call it as a confusion matrix to see how good our models do. So we see there is an error of 3 here out of 50. There is an error of 3. So 47 values are being calculated fine, and hence the accuracy of this model is 94%. To tell you quickly again what I did here, I used my neural network model to predict what species each of my flower belongs to in the testing data set. Then I compared it with the actual species which were present, and finally I get this table which tells me that I have an accuracy of 94%. Okay, so weights will change according to the error, whatever the error is. The end aim is to get a threshold of 0.01, passing whatever weights possible. So it is entirely possible that when you run this algorithm the second time, if you remember here, we had done this with 125 steps. Okay, when you run this the second time, it may take lesser steps, it may take more steps, but towards the end, your result will be the same. Okay, because the algorithm will stop when it achieves a threshold of 0.01. Just to tell you, I'm running this algorithm fourth time since yesterday. Once it has run with 300 steps, once it ran with some 95, 96 steps, and once it is running with 125 steps now. But your end accuracy will be the same. The same confusion matrix you'll get no matter how many times you run the same algorithm, because it will use the threshold to stop, and the weights can be anything. Okay, so for today's session, I'll just be doing an exploratory data analysis that will help you just see which variables should be used and which should not be used. Towards the next session, we'll try to actually solve it to see which what is the output that each of the algorithm throws. Okay, I'm importing the data set. Okay, so when I'm viewing this data set, it contains approximately 3000 or like 2940 rows, and it has 35 columns. Structure is just an additional step to see what the structure is. So we have a total of 2940 rows, and then we'll now go to each of the variables individually. So when I start off with the attrition variable, one thing to note here is that these variables have been arranged in an alphabetical order. So you need to, if for better understanding, you might want to rearrange these columns so that similar columns are together. I haven't done that, but maybe you can do that, arranging the similar columns next to each other so that it becomes easier for understanding. So we see here when we start off with attrition, so there are a total of 2940 employees, out of which 474 had an attrition. Okay, so that becomes 474 upon 295. 2940. So approximately 16% of people had an attrition, and we'll see what impacts the attrition of these 16% of the employees. Okay, so we'll start off with each of the variables one by one and see whether or not that variable should be included here. So I'm starting off with the age, which is the first variable here. So you see the minimum age is 18, the maximum is 60, and the median excuse me, the median is 36, which is somewhere in the mid. So the data looks like not being very skewed. We do a box plot of it and we see that it looks like a normal curve, the age. So there are people from the ages 18 to 60. And the data is normally distributed. Now I'm trying to see so this is another way. I did a box plot, and this is another way to do a clearer histogram. We could have done it using the hist function as well, but you can also use ggplot to do a histogram, which gives you a more precise histogram to see the distribution of the age. And finally, I'm again using ggplot to see the impact of age. So what I did here was, for the continuous variables that were there with the data set, I'll try to see what is the impact that those variables have. So when I do a ggplot of the age, I get an output something like this. So what this tells me is the pink color shows the employees that have an attrition and that do not have an attrition, and the blue color shows the employees that have an attrition. So what this tells me is that the people who have an attrition or who had an attrition are belong to the age somewhere from probably 28 to 39, and the ones that who do not have an attrition have an age somewhere from 31 to say 43. What this tells us is that when you're seeing just the age variable alone, there is a difference in the ages when the people have an attrition or not. So people in the younger age groups are more likely to have an attrition compared to people in the larger age groups. So this helps us understand that when we see the impact of age alone with attrition, so age is an important variable when we are trying to study attrition, because there is a significant difference with this graph. So the age should be included as a variable, as an input variable when we are trying to do the modeling. Okay. Next, we'll go to the second variable, which is business traveler. So it is a categorical variable that tells us whether or not a person travels for business and how often he travels. So out of the 2940 employees that we have, so we see that most of the employees travel rarely, and then we'll try to understand whether or not traveling has an impact on attrition. So since this is a categorical variable, I just created a simple table to see if there is an impact of business travel and attrition. So we see the ratio that you see between a no and yes here. So for non-travel, the ratio of 276 to 24 and 416 to 138 and 1774 is to 312. This is almost similar. There is no much difference. Let me do an actual numbers. 276 by 24. 416 divided by 138. 1774 divided by 312. So there's not much difference in the people who travel to see whether or not they have an attrition. So you can choose to ignore this variable because it doesn't look like it is having an impact on whether somebody or not has an attrition from the organization. Okay. Age we saw has an impact, but the business travel does not look to have a significant impact with the business travel does not look to have a significant impact with attrition, so you can choose to ignore it. Okay. Similarly, we go to next the daily rate. So daily rate is again a continuous variable which shows the rate at which an employee is being paid on a daily basis. So when we see a summary of it, it is again a continuous variable, the minimum being 1022 to a maximum being of 1500. When I do a box plot, it looks like a normally distributed data, and you can also see that from an histogram as well. But a good thing to see here is if I do the impact of daily rate on attrition, probably the daily rate does not have a very significant impact. Let me go back to the histogram again to show you. So see, almost all of the daily rate is uniformly distributing, meaning to say that across all the 2,900 employees that we have, the daily rate was evenly distributed. And when I did a comparison of people who ate right or not from the organization based on the daily rate, there is no significant difference. There is a very small difference here. If I zoom it out, so this is 400, so 600, so this is somewhere around 450 or so. So there's not a very significant difference compared to the range of daily rate that I have. There is not significant difference in the daily rates of people who have an attrition or not. So even daily rate you can choose to ignore when you're doing the modeling. Okay, with age we had a significant difference. With daily rate we do not have a significant difference. And also we saw from the histogram that the daily rate is not very varied. It is almost constant. The frequency of the daily rate within the employees is almost constant, so it doesn't look like having a very significant impact. So you can choose to ignore the daily rate variable as well. Okay, next we go to the department, which is a categorical variable. So we'll just see a summary of it. Okay, so see, this is significant here with the human resources. 1656 divided by 266, and so this is evident from the data as well, but I'm trying to show it more clearly. Okay, so with the department as well, the ratio between no and yes is almost similar. Okay, the people who at right versus the people who do not at right is again similar. So department again you can choose to ignore, because there is no significant difference with respect to, there is nothing like people of a particular department have more attrition compared to people of other departments. So you can choose to ignore this variable as well. Okay, so then, or maybe, okay, 284 is also okay. So then you see that there is a different, significant difference with the other departments. So if you see that for a particular department, the ratio between no and yes is different for a particular department compared to other departments. So then you say that people of that particular department have a more attrition rate compared to people of the other departments. So that will mean that that particular department has a significant importance when you're when you're creating a model. That department variable has a significant importance, and hence it should be included. But with the current data set that we have, there is no significant difference with each of the departments, so you're okay to ignore it. Okay, and this is what happens when in the industries when we are actually working. So this is again a data set with 35 variables, but this is again not huge. We had actually worked with one of the data set that had some around 170 variables or something like that. So we need to most of the time gets spent in doing the exploratory data analysis only, because the models that you're creating, like the neural network I created here, is a two-liner command that you can execute within seconds. If the data is huge, that command will take a minute or maybe 1.5 minutes to run, but then it is again a two-liner command that can be executed quickly. Most of the time that goes in the organizations is doing the exploratory data analysis, and that needs to be done for each of the variables here. So here with
Yeah.
this data set, I haven't done so I had seen an overview of what the summary was. So this doesn't look like a data which contains outliers. So in the actual data that you'll see, there'll be outliers as well. So how will you understand whether or not the data has outliers is by studying the individual variables. Okay, you study the individual variables. Whichever variable you see looks like having an outlier, that needs to be treated. If there's a missing value within a data set, that needs to be treated. And finally, using the summaries of each of the variables, you need to decide whether or not that variable needs to be included in the data set. So I've done that for each of the variables. So since this is clear now, I'll quickly run through all the variables. So when you do this exercise for the mini project that you're doing, repeat these steps in a similar manner for each of the variables. Then you also have this distance from home. So that tells the distance of the employee's home from the office, which is a number from 1 to 29. And if you zoom this out, this is a very intuitive as well, that people who have, so distance from home to your office is a significant factor, and that is also evident from the data. So you see people who have more distances from home, like the yes is in the blue color. So people who have more distance from home are more likely to have an attrition compared to people who have lesser distances from their homes. So distance from home is a variable which should be used as a factor for impacting attrition. Next is the education level and the education field, which are categorical variables. So we'll just see a table of them here. So with this table, I am not doing the actual ratios here, but do the ratios of these variables to see if a particular education level you notice has more attrition compared to other education levels, then you need to include education in the as an independent variable. But if all the education levels behave in the same way, then you can choose to ignore it. Similar is the case with education field as well. If there is a significant difference between the attrition of yes and no for any particular education field, then it should be used, otherwise it should be ignored. Now one thing to see here when you do different models, like for example if you're doing a random forest or a neural network, so even if you do not do all these steps, the model will run. So especially when you're doing a random forest and you do not do these steps, the model will run, and the random forest and for that matter cart also, both of these algorithms choose the best variables by themselves. Okay, because they use the, like cart uses the Gini gain concept, so it sees all the variables itself as well, and chooses which variable is good, which variable is not good for splitting. So with those algorithms, even if you don't do these steps is okay, but doing them is a better thing. But if you don't do them is okay. But with neural network, if you simply pass all of the variables at once, if you pass all of the variables in the neural network model, the model will run, but the accuracy will not be good. So this step becomes essential when you're doing a neural network to achieve accuracy. Okay, because with neural network there is no particular algorithm to decide which variable is important, which variable not important. Whatever the variables that you're passing through the neural network, it will learn from all of the variables. The back propagation, the error rates, the gradient, everything will be calculated on each of the input variables, and it has no method to decide which variable is good and which variable is not good. So then the model accuracy is not very nicely. So very nice. So especially when you're doing a neural network, do this as a mandatory step. Okay, and unless you do this, you won't be able to also see. So there could be some variables which are correlated, there could be some variables which are intuitive, there could be some variables which can be calculated from each other. So you won't be able to understand that until you do an exploratory analysis. So see, like for example, I show you one of the variables here. For example, this employee count. So employee count is doing nothing, but it is like telling whether or not this employee is distinct here, just to check that there are no duplicate entries. So that this variable doesn't make sense when you're passing it to a model, because just by doing a quick check once on this particular variable, you can decide whether or not there are unique employees or not. Random forest doesn't know that. So random forest will try to consider in one or more of the trees that it is creating. Random forest will try to consider it as a variable, wherein you yourself know that it is not important. So why just pass it at all? Okay, similar is for one more variable, which is I think over 18 here. So you have an age variable, which is enough to calculate the impact of age, and the over 18 anyway contains all y values. So that it is not significant. The random forest doesn't know that it is not significant or it doesn't make sense. So I just pass it at all. Okay, because in case it sees that it is significant, but that it is not significant, so it is advisable that you do not pass such variables at all. There's another thing I'm showing you for an example with which you should avoid when you're doing the modeling in addition to the data set. Say you have a salary of, like you had monthly rate here, say you have salary of January, salary of February, salary of March, and so on till salary of December for the employees, and then you also have a total salary in your data set. Assume that the salaries for each of these months are different, they are not the same. Say this is 1000, this is 1200, this is 1150, this is 1300, and so on. So these are not same, and then you have a total salary which is sum of all the salaries, and you have all the variables here. Now these variables may not necessarily be correlated. It is possible that for one employee, probably the salary of February was more. For the second employee, maybe the salary of February was lesser than January, the salary of March shooted for any reason, and then the total salary will be accordingly. So if you see salary of January, salary of February, salary of March in this data set, it will not be correlated. But the important thing to note here is that total salary contains the essence of all these variables. So when you have a data set something like this, ignore all of these variables, include just the total salary. Okay, so this is an additional step apart from correlation. The salary of Jan and Feb may or may not be correlated here. The salary of Jan and total salary may or may not be correlated here, but then the total salary captures the essence of all of these variables. So if you have a data set something like this, ignore all of these variables, include just the total salary. So I did this for all the variables here. Like we have the employee count, like I showed. So employee count is just to see whether or not there are duplicates in the data, and there are 2940 employees, and the count is always 1 here. So unless you do an analysis of this step alone, you won't be able to determine this. So this variable has no importance at all, and you should ignore this. Okay, so I kind of did that for all the variables. For environment satisfaction, this again is a categorical variable, and you can decide whether or not to include it. Same was for gender, it was a categorical variable. Same was for the hourly rate here. So you see, the hourly rate, it is very much similar. Whether or not there is an attrition, the hourly rate is very much similar. There's no difference. So don't include this variable when you're doing the modeling. One more thing I wanted to show you was what we had seen earlier as well. So I'm doing this for all the variables, and you can decide whether or not to include them. Okay, for the monthly income. So you see the summary of monthly income, it ranges from 1009 to say 20,000 approximately. When I do a histogram of it, okay, so we had seen this when I showed you the air pollution well regression example. We had seen this, but see, the histogram of monthly income is highly skewed. Okay, so this again should be considered before you do the modeling, that there should not be any skewness in the data, because if it's not normally distributed, the data will be biased to learn more from the monthly income. Like here, probably the monthly, more people have monthly income in the ranges of probably 2500 to 7500 contains most of the people. So the model will learn more from the employees that have salary ranges between 2500 to 7500, and lesser from the employees that have salary ranges in the other that have salaries in the other ranges. So the data should also not be skewed when you're doing the modeling. So when I do a log of it, the skewness gets removed, and hence when you're passing this variable, you should not pass the monthly income, you should pass log of monthly income as the independent variable before doing the modeling. Okay. So couple of things to check is, one is the missing values, one is the outliers, then see whether or not they are correlated, the variables are correlated. Then also see what I told you in the example, if one variable can be computed from the other variables, then use just one of them. Then also see whether or not the data has outliers or not. If it has whether or not the data is normally distributed or not. If it is not normally distributed, do a transformation and then pass the transformation as a variable rather than the individual variable. Okay, so monthly income you see has a significant impact on the attrition. The people who have a smaller monthly income and the people who have a higher monthly income. Okay, I've done that for all the variables. This is again over 18 variable, which contains all Y's, that all of the people are above 18. So that is a totally non-significant variable. We see one overtime variable again. See, this tells you that overtime out of 578 and 254, and then this is approximately 1900 and 220. So people who do overtime have a more likelihood of having an attrition rather than people who do not do overtime. So overtime is a significant variable. The same thing what we saw for monthly income also applies to percent salary hike. So see, this again is a heavily skewed data set, so you need to do a transformation of it before you actually pass it. So I use this box-Cox test which we had seen earlier when we did regression. So I used the the lambda value here, and when I plotted transformed value of the percent salary hike, the skewness looks like having been removed. So then instead of passing the person salary hike, I should be passing a 1 upon person salary hike as an independent variable. Okay, so you need to do that for all. One more variable here was for standard hours, which is 80 for everyone. So you can ignore it. Do that for all the variables. Okay. One easy way to check for the missing values is a command that I've put here. Either you can do it for all the variables one by one, but this is one simple command to check the missing values all at once. So when I run this command, I'm just checking whether or not there are any NAs in any of the values, and I'm creating a matrix based on that. So it shows you for each of the variables whether or not there are any missing values. Okay, so it shows 0 0 0s in all of the values, means that there are no missing values in any of the variables.
Thank you.
Okay,
Okay,
thanks.
thank you.